Before I start with my talk, I would like to just introduce you to the task 13 of the Power PV system, Power PV Power System program on behalf of the operating agents Ulrike Jahn and Boris Farnung from Germany. So generally, we live in amazing times. So the PV market is still growing. Every year we see an increase in this market growth. And that is actually setting the scene for us for the Power PV Power System program. So because what we see now is that PV is moving in a lot of places. So we see fast technology progress. We see high or big installed capacities. We see record prices and record levelized cost of electricities. We see an increasing competitiveness of photovoltaics in the market in general. We see new business models. We see broader applications, different customers. We see it moving into the overall energy system. We are constantly moving towards the terawatt era and become mainstream. And that is actually an amazing thing. When I remember back when I started my research career in 2003, people discussed about PV becoming mainstream, I don't know, in 50 years or so. So actually it happened quite a lot faster. So what is the power, the PVPS in a nutshell? So it's an association having 32 members, so mostly countries, but also 4 associations. And they form a truly global and unbiased network of PV expertise, representing all main stakeholders in R&D industry, implementation and policy. And let's say the members are covering also a large majority of worldwide production, application and markets. We work along the value chain. So in our network, we have researchers, we have manufacturers, companies, and also operators dealing with along the value chain of photovoltaics. And so what is our role? We look into the present and future of photovoltaics worldwide. We try to identify and understand relevant issues for large-scale deployment of photovoltaics. We collect and exchange facts and experience. We analyze precisely and draw appropriate lessons learned, and we communicate all the findings in a clear and targeted way. And the benefits are that we provide advice for different stakeholders, including policymakers. We try to accelerate the development and learning in the market and prevent errors to be repeated. We identify successful policy approaches and business models and try to provide long-term market, environmental and policy insights. And in general, expand and accelerate the deployment of photovoltaics even more in the future. So right now we have eight active tasks in the PVPS program. And I'm part of task 13, so which deals with performance, operation, and reliability of photovoltaic systems. Within task 13, let's say we have 3 major topics. Our first major topic is to look more into detail into new module concepts and system designs, especially questions related to quality and reliability of these new concepts and designs. We do a lot in performance of PV systems, especially the analytics of the available data. And also we look on how we can improve operation and maintenance of PV power plants. Let's say in the last year, we were quite busy, and overall 12 technical reports have been published on different topics within these 3 fields. And today we are focusing on the designing new materials for photovoltaics topic, which got published 2 months ago. And so my talk, I will start with motivation, benefits, and opportunities for new material and module developments in photovoltaics. And then Laura will continue and will go more into detail of certain PV module components. So this is the report I'm talking about. You can find the link for downloading it. Download is free. So please go there and take a look. I think it's worth your time. So let's start. First, I want to show you some quite interesting results that colleagues of mine in Austria have presented last year at the European PV conference. So we have a very interesting system installed in Austria. It's installed on top of a mountain, so I think in 2,000 meters height. And the system was installed in 1988, so it's like 33 years ago. And when you look at the annual degradation of these modules after more than 30 years, you can see actually they're performing quite well. So the best performing modules from Kyocera, they seem like new. So you don't see any glass breakage, cell breakage, any form of discoloration, corrosion, whatever. And in more than 30 years, they have only 6.1% power loss. But also the other modules from Siemens and Arco, that actually, where you see, for Siemens, you see discoloration, and for Arco, you see actually quite severe corrosion of the ribbons. Still, the overall power loss is quite low. So like 30% for the Siemens modules and 20% in 30 years for the Arco modules. So this is still quite acceptable, even in these times. So that was the first interesting thing. The second interesting thing is when you look at the system here. So here you see all three types of modules. And then you see actually, same locations, same climatic conditions, same environmental stresses, but different degradation patterns. And what we learned from this is that actually degradation modes of PV module and degradation rates depend strongly on material interactions. So they depend on the composition of your PV module. So depending on which materials, which components you use, you will get different results, even though you have the same stresses. And so the bill of materials of PV module is very important for understanding PV module degradation modes. And to make the work for us easier, it would also be quite beneficial that this bill of materials is reported, and not just like the electrical data of the system, like the flashing results and the power output you get. So because when you know this on the label, then you may understand degradation modes easier. So the question is that I asked myself and that we discussed in several groups, so why aren't PV modules built like this anymore? So very resilient, very long lasting. Yeah, the answer for that is quite easy, because what happened in the last 20 to 30 years, especially in the last decade, is we saw a massive decrease of price. So like for every doubling of the production, we saw a price reduction of 25% at least for the last 40 years. And with that also, the average efficiency of the modules increased significantly from like below 10% to now, like we have more than 20% efficiency for monocrystalline silicon PV modules. And as you see back here, these modules had like a nameplate power of like 50 watts per module. And where we are now is like we are getting into 500 watt modules and higher. So what we saw is a big change in the market. And even though the design of the PV modules remained similar, so we always have glass encapsulant, the connected cells, the ribbon connected cells, and the backsheet or another glass layer, the materials that are used, they evolved. And Michael Woodhouse and colleagues from NREL actually prepared this really, really wonderful chart for the new PV manufacturing report. And this is just to show you how much actually PV changed over the last, let's say, 40 years, where we started with very small circular cells, got into small pseudo square cells. And right now we have like these very big pseudo square cells. We are going to half cells, and you just take a look at the watts per that we have and the module sizes that are typically. So like from 40 to 100 watt modules, now we are having like 600 or like 400 to 500 watt modules currently. And when you take a look into future, actually with multi-junction modules in tandem, cells that we actually will get modules with like 1 kilowatt of power, maybe in 10 years. So just imagine this, what happened. So what have been the motivations for all these changes for the new materials and new module designs? I would say the biggest motivation was always decrease of levelized cost of electricity. So either it's cost reduction or performance improvement. And what we saw constantly was like a reduction or replacement of expensive materials. So in general, solar cell thickness went down, silver content went down, glass thickness went down significantly. We also saw like expensive materials like fluoropolymers have been started being replaced by more, let's say, more economic materials. So all of that helped a lot to get, let's say, a cost reduction. And this is a process that is still ongoing when you take a look at the projections done by the International Technology Roadmap for Photovoltaic, for example, where they foresee still doubling of the silver content reduction in the next 10 years, depending on cell technology. So what were other factors, or let's say approaches for cost reduction? What we saw was generally an acceleration of the manufacturing process. So we started with standard cure EVA, then there were a fast cure EVA popping up 15 years ago. Then we had ultra fast cure EVAs 10 years ago. Currently, we are getting into thermoplastic encapsulant that can be laminated with lower temperatures and lower times. So everything that gets the module production time down a little bit. And then we had several, let's say, changes and new developments that actually promised a performance increase. So when we are looking at the interconnection, the cell interconnection, we saw going from 2 bus bars, 3 bus bars to 5, 6, 7 bus bars, and all of these multi-wire systems. And let's say one main motivation for the performance increase was the reduction of the resistive losses and the cell shadowing. Another thing the industry and R&D was working on, new encapsulants and new backsheet materials, for example, with enhanced optical properties. So like on the right-hand side, you can see when you compare 2 different backsheets. So the first was a laminate, the other one a co-extruded backsheet. Both of them have a white color, but the polypropylene is wider than the polyester-based backsheet. And because of this higher back reflectance, we can increase like up to 2.5% higher power output in a PV module just because of the back scattering of the light. And the same goes for encapsulants. So I think Laura will show you something about this. Yeah, and also what we saw in the last years was a continuous increase in wafer size and also leading to production-related cost decrease. Another motive for bringing in new materials and new module designs is sustainability, and connected to sustainability also certain legal regulations. So we see especially in the European Union, there is currently a process for eco-design of photovoltaics running, and I think it's nearly completed, that at the end we get some sort of eco-label for PV modules that have, let's say, more sustainable components and gives you, let's say, more sustainable production processes. We are starting to talk about recycling and increasing the recyclability of photovoltaics, because we are putting out hundreds of gigawatts every year, so there are billions of modules putting out, and at the end of life we need to start to think what to do with all this amount of material and all these modules. And also we see, at least in the European Union, legislation, for example, the ROHS legislation for electrical devices, for example, that rare or harmful materials should be replaced. And for example, usually lead is not allowed anymore in any electrical device. And photovoltaics is just one exception here. And we don't know if this exception will, let's say, continue forever, or maybe in a few years the European Union will say, no, you have to get rid of the lead and replace it with another material, and so actually the whole interconnection needs to be changed, especially the solar material. Yeah, and another big motivation for new materials and new module designs is actually when you have new technological requirements. And here we are looking mostly into what I already mentioned, new wafer technologies or bigger wafers. In the last years, we saw quite a change in cell and interconnection technologies, and also new module designs were brought up. And what we see right now is actually a very big shift from the aluminum BSF cells going to PERC and heterojunction that will become the new dominant cell technologies. We see like half cells will gain more market share, and we also see the module sizes increase. And for example, especially for heterojunction cells, which are more sensitive to, for example, temperature-induced stresses, these cells are predominantly interconnected with multiwires, which is a totally new approach for interconnection. But we also saw that structured foils, for example, for back-contacted cells are gaining more attention, and also shingling will be a topic for the future and getting more important. And all of these technologies combined have one thing, and they lack the long-term outdoor experience. So yeah, we know a lot about indoor tests, but we still don't know how these shingled modules and multi-wire connected modules will behave actually in 10 years and 20 years. What's also very interesting, what we seeing right now in the market is some sort of diversification. So I would say up to now, still this one module type fits all approach is quite prominent. So like, yeah, you produce one module and you install it everywhere in the world. But what we know is actually that, you know, depending on the location you are and the microclimatic conditions there, you will have very different degradation rates in, let's say, in certain regions. And here you can see, this is from an European project, from Solar Train project, the map actually how big the degradation rates are to be expected in certain climatic zones. And you see actually, yeah, tropical regions are the most severe for photovoltaics, so corrosion is a big issue. And maybe it makes sense to diversify like module types and let's say build specific module types for certain applications, certain areas, or also let's say have cheaper modules that are just installed in moderate climates where you don't need, like, for example, this high corrosion resistance. And that is what we actually see. So now more and more like approaches like this surface on the market. So we see, especially for desert zones, like for example, here's a picture of the Atacama Desert in Chile, where we get dedicated module designs just for deserts. But also what is a big topic right now is integration of photovoltaics. And by integration, I mean integration into nearly everything. So we talk about vehicle integrated PV. We talk about building integrated PV. We talk about PV integrated in transport infrastructure. Like this is a very nice Austrian project with, I think, in cooperation with Germany and Switzerland, where they want to make like roofs across highways made of photovoltaics. We talk about integration of photovoltaics in agricultural land, and a very big topic also, floating PV. So what are the challenges for all these kind of new materials, for these new PV modules? Yeah, the challenge is actually here schematically. So this should be a cross-section of a PV module with cells, interconnects, glazing, encapsula, and backsheet. And you see we have a lot of external and internal factors, stresses that are acting on the PV module. So from irradiation, temperature, humidity, atmospheric gases, and mechanical loads. And of course, then, as I already said, the composition of the PV module, the materials you use, and the processing effects, they actually also influence the long-term behavior. How do they do that? The materials have to withstand all these stresses at the same time for a very long time. And actually, photovoltaics is or let's say PV modules and PV materials have to withstand an extremely challenging microclimate with acting stresses all at the same time. And when you change just one component, like you put in a new encapsulant or put on a new backsheet or some new, let's say, interconnection material, you can change the whole equation here, you can change the whole set of reactions here and change your degradation behavior significantly. And what I see is that will be, I think, the interesting part, at least from my point of view as a reliability engineer. What will happen with all of these new materials? And I have the feeling we will see a lot of these, like I would say, compatibility issues in the future. Like when you combine the wrong materials, that you will have problems with adhesion, and we will see more delamination. For example, when you have like new encapsulants and combine it with a standard backsheet, but the backsheets are usually optimized towards adhesion for EVA, which is the standard encapsulants, then maybe you will get some problems. I would say yellowing in general, discoloration will be a big issue. Has always been a big issue, but with new material combinations, you will get new possibilities for this yellowing, and the same is for like corrosion, because we see a broad variety of new ribbon materials, new interconnection technologies, we see new encapsulant films, new backsheets. All of these are influencing, let's say, corrosion. And what we saw in the last 10 years, we saw also an emergence of new degradation modes. So like until 5 years ago, just my assumption, nobody spoke about LETID, so light and elevated temperature induced degradation. 10 years ago, it was all about discussing PID. And all of these issues came up with new technologies, like with new cells, new cell designs, with new encapsulation materials. And because of this, and because we need to check compatibility, we have a constant need for adaptation of test methods and also of the underlying standards in order to, let's say, catch all of these weaknesses in a very early phase. Because when you look at typical failure scenarios of silicon PV modules, then you see you have infant failures, you have midlife failures, and you have wear-out failures. Okay, wear-out is mostly dependent on material degradation. It can be delayed to some extent, for example, but it cannot be avoided totally. So we will always have material degradation. But infant failures are very often correlated to bad lamination, like bad processing. So, and also midlife failures also are very often let's say correlated to bad component selection. And many of these failures can be avoided by extensive R&D, by extensive quality and reliability testing. And this is still a thing that the PV community has to do, and that, for example, other industries like the car industry are way ahead, because they make much more, for example, long-term reliability testing than photovoltaics, even though their product is not there for 25 or more years. So how can you do testing? Let's say that's what that's what we use usually in polymer engineering. So we have some sort of test pyramid. You start with a material. There you can test a high number of specimens at a very low cost and effort. And then you go up, you test components, films, you test laminates, you test mini modules, up to full-size modules. But the higher you go up into your testing pyramid, the higher the cost and the effort of testing. Nevertheless, you need to cover all of these levels, because you learn something different on all of these levels. And it's an effort, but it's an effort you need to do. And actually everybody in the PV community should do, in order to avoid unexpected, for example, unexpected failure modes. And just to summarize, I want to present you one of these unexpected failure modes. And I think all of you have heard of the polyamide backsheet failure. So these co-extruded polyamide backsheets have been introduced into the market in 2010, unfortunately by an Austrian company. And it was a big success, instant success. So what was the motivation for this backsheet development? Yeah, there was a problem with the raw material supply for back then standard backsheet composition, because back then the so-called TPD backsheet was dominant, and the T stands for Tedlar, that's PVF, polyvinyl fluoride, and there is only one manufacturer, as we all know of this, and there was some sort of, let's say, market shortage there on this material, and so there was a big incentive to develop new materials, and that happened. So this material was introduced, and then in the next 5 years, I don't know, estimations around 10 to 12 gigawatt of PV was sold with this polyamide-based backsheet. Yeah, and then in 2015, this happened. Depending on the locations where the modules have been installed, the modules started to show different types of backsheet cracks after some years. So let's say in more severe climates, after 5 years, in Austria, we see it after 8, 9, 10 years starting to happen. But what we learned, it happened, yeah, for nearly all the modules. So first estimations done, let's say by different institutes, we believe that, yeah, every backsheet will crack sooner or later. So why haven't these failure mechanisms not been observed in the lab? Because this crack formation is a two-step process. First, we have some sort of reduction of the fracture toughness due to long-term exposure at high temperatures and UV radiation. And then we have continuously mechanical and thermomechanical loads on the PV module. So think of the daily temperature changes causing, let's say, stresses because of the different thermal expansion behavior. We have wind loads, snow loads. So all of that is working on the PV module. And you need both factors in order for crack initiation and crack propagation. So what was done? Yeah, back then, single stress testing was state of the art. So they made materials, the films, they made mini modules, put them into the climate chamber, in a UV chamber, in thermal cycling. But it was never the same module going in this test. It was one module for damp heat, one module for UV, one module for thermal cycling. And the problem was, with all these tests, you have either just reduction of fracture toughness, but no mechanical impact and no, let's say, driving crack propagating force, or you just have like the mechanical loads, but no material damage that you need in order for the crack to being initiated and grow. So you couldn't catch it. What should have been done? Yeah, actually make a module, put it into damp heat tests, then put it into the climate chamber, put it into some thermal cycling, and then cracks will happen. So you need some sort of sequential or combined stress testing. And that's what's happening right now. And that's actually how industry adapts to this. So some years after these cracks first occurred, several research groups, especially in the US, they went on this problem and tried to replicate this backsheet cracking. And let's say two different groups, so one from NREL with their combined accelerated stress test, and from DuPont with their sequential stress test, both succeeded in creating, recreating these cracks after accelerated indoor test. It still takes some time, several months, in order to create these cracks, but they managed it. And right now, let's say, we know how to test backsheets, and these experiences are also, let's say, being introduced into, let's say, newer versions of the standards, just because we learned about this. And this is the constant challenge that we have, like with new materials and new components for PV. So to conclude, there are several motivations for new materials and module design. So most important, it's the decrease of LCOE, so cost reduction and performance improvements, but also new technological requirements, sustainability issues, legal regulations can be a motive for new materials. The challenge is always the same. The long-term stability of a PV module is determined by the bill of materials and their interactions. And therefore, each material combination must be tested thoroughly before introduced into the market in order to avoid such unexpected failure modes. And also, as I said, as I showed, single stress testing, as is done very often in industry still, often does not reveal certain degradation modes which are observed in the field. So we need more combined and sequential stress testing in order to check these kind of failure modes. I foresee that the check of compatibility of PV module components will get more and more important in the future, especially as the variety of materials and components will grow. And we will see new degradation modes we could not think of right now. And because of that, we have a constant need for adaptation of test methods and test standards. And in general, design matching of components and materials will get more important because they may reduce degradation rates or avoid certain known degradation modes. And in general, I think that's a sentence I put on most of my presentation. A better understanding of PV module and material degradation processes is a precondition for a successful development of new components and reliable PV module designs. And with that, I want to thank all of you for your attention, and also to all the contributors that helped me and my editor colleague, Josh Stein from Sandia National Lab in putting together this report. And with that, I want to give over to Laura, and she will go more into detail into some recent changes within PV modules and show you some results on new materials. Thank you very much.
Thank you, Gernot. So I'm going to share my screen here, and we're going to talk about materials innovations in PV, so new things that are happening in PV and the challenges that causes for reliability. So as Gernot was showing, there's a lot of changes and development in PV, and it's rapidly growing. So we have new cell types, new cell sizes. We're increasing bus bars to like 9 bus bars. Manufacturing is changing, and there's new applications. We're integrating PV into buildings or into agrivoltaics or as floating PV. So these require new materials to increase performance, lifetime, and durability, and for these new applications, but also we need to reduce cost in often times. So to prevent large-scale degradation or failure in these new materials, we need a good understanding of degradation. I think Gernot and I were on the same page with that you need to understand what's actually happening fundamentally in these materials. And this helps you make design choices, and you need to be able to test multiple different designs and different material compatibilities, as well as test these under multiple stress conditions, as well as in the real world. So I'm going to go through materials from as if we were looking at the PV module. So we're going to start at the front, go to cell metallization, and then go into encapsulants and backsheets. So many applications need lightweight PV. This is, things like building integrated solar, you need a more lightweight PV. So you might in fact need a flexible front sheet that's made out of a polymer instead of glass. This also makes the material thinner. So these materials are difficult and they're not necessarily suitable for PV at this time. There's issues in long-term stability, there's thermomechanical behavior and compatibility with the encapsulants, and they need to be stabilized due to photothermal degradation. So what I'm showing you here is a study of 15 different possible front sheet combinations. And there are different costs where ETFE is much more durable, but it's also more expensive, where PET that's not really stabilized would be relatively cheap, but would have poor performance. And then what you see here, looking at the solar quantum efficiency weighted transmission of these materials, is that all of these materials have very different performance under different degradation conditions. So they have a lot more transmission losses here at 70 degrees C than 90 degrees C. And they have very different behaviors. So this is something to understand when we think about PV modules out in the real world, there's different climatic zones, there's different weathering conditions, and maybe we choose different materials for different locations because of that. Because it's hard to design a material that performs well across from Antarctica or, northern Canada down to Australia. So UV durability is a concern for these materials, and these still need to be incorporated into PV modules for exposures and combined stressor tests and some real world data from them to understand the durability. So next we're going to talk about encapsulants. So we have the front sheet, which is typically glass. Now we can look at some flexible front sheets, but now we're looking at the encapsulants. So right now, most PV modules out there are made with EVA. That's the huge market share of PV modules out there, but that's starting to change, and PV manufacturers and material manufacturers are making different types of encapsulants. So I'm going to talk a little bit about POE and TPO, which are new types that are coming out. So when we think of POE and TPO, these are polyethylene copolymers. There's no vinyl acetate group, so that's different than EVA. So you shouldn't get formation of acetic acid with these materials the way you do with EVA. So polyolefin is a cross-linking material, and TPO is a non-crossing material. TPO generally has a higher melt temperature than POE, but you can have shorter lamination times. Generally, they have higher volume resistivity than EVA and lower water vapor transport rates than EVA. So they generally have similar optical transmission profiles. And one nice thing about these differences in encapsulants is we don't really need different ways to analyze them, because the analysis of them is very similar to what we would be doing for EVA. So here's a study here where we're looking at different types of POE and different types of TPO. And this top figure here is POE these materials at baseline and then at 4,000 hours. And what you can see is on this UV edge, we start getting loss of UV transmission from the different materials. So you can see POE2 drops slightly, TPO1 drops a lot. And then what you see here is that TPO2 has a much higher haze. So generally TPO2 has much higher crystallinity, which would cause that much higher haze value just to start with. And it has a reduction in haze over time, as well as TPO1, which suggests that they are actually having a change in crystallinity during these exposures of irradiance. And they both slightly yellow, or TPO and yellows much more than POE in these examples. So that's this top row of figures. The bottom row of figures is what we see is that these are little 6-cell mini modules that were exposed to 0 hours, and they have POE, TPO, and EVA, and then to 3,000 hours of damp heat. And what you see here in these bottom ones is that there's actually corrosion at the grid lines with EVA, but not with POE and TPO. And this is because the EVA is hydrolyzing and causing corrosion of these grid lines, but we don't see that in TPO and POE. So this suggests that they're not inducing that same degradation mechanism, and they don't have that acetate group. So another thing here, this bottom figure is mini modules exposed to damp heat and thermal cycling. So they were in damp heat and then switched to thermal cycling afterwards, and then back into damp heat. And the x-axis here is the number of hours they were in damp heat. And these are 3 different cell types encapsulated together. And then they have UV cutoff EVA and UV cutoff POE, white EVA and white POE. And what you see here in this bluish kind of color is white EVA encapsulant. You see huge power losses in those mini modules. And only in ALBSF cells. We don't see these in the PERC, 2 different types of PERC cells. So what this tells us is that the degradation of this white EVA encapsulant actually caused much more degradation to the ALBS cells than the PERC cells. So there's material compatibility things that we need to account for when we're thinking of building up into our whole PV system, that some materials might work better with different cell types. This white EVA was causing degradation due to the TiO2. If it's not a high quality TiO2, rutile TiO2 actually becomes a radical and starts attacking the polymer backbone and causing, in this case, would have caused much more acetic acid formation. And then another type of encapsulants that's starting to be looked at again is silicones. So PDMS and its derivatives were historically used in the 1980s due to its stability and durability. It's reported in the PV literature. We also see in other areas that these silicones are pretty durable. However, there was a cost problem, so it was limited use in PV. It was applied as a viscous liquid, so it was hard to do in line and without as much cost. But what it seems is the silicones provide corrosion protection, they don't really have discoloration, and they don't really have PID, and they still have high optical transmission in the UV region. So a new silicone encapsulant sheet has come out so that you can laminate it under conventional vacuum heat lamination, has similar properties of the previous liquid form. But we still need reliability data on, again, mini modules, coupons, and full size modules. And this figure here, what we see is that we have the top line is EVA as the encapsulant front and back. B is silicone front and back, and then C and D are different front or backside silicon. And what you see is that with just EVA, we still get this corrosion, this acetic acid formation, and it causes corrosion in our cells. You also see it when EVA is on the top, but not necessarily when EVA was on the backside. So this is an opportunity potentially to have different types of encapsulants together, and you may be able to lower the cost by using EVA, but potentially on the backside. And there's still more research that's needed in this area. So next we're gonna think about metallization. So metallization still is primarily done with silver screen printing, paste, which is like 95% of the PV market. So something new out that's being discussed is this metal matrix composites that are added here to the grid lines, and they're multi-walled carbon nanotubes, and they can actually bridge cracks in metallization. So if there is a fracture in your cell, that can actually cause a fracture in the metallization, and that causes power loss as well as a root cause of hotspots. So one way is to potentially mitigate or correct these cracks with these multi-walled carbon nanotubes, in which they actually can help self-heal cracks or electrically bridge those cracks so that you don't get the drop in power loss. And this figure here on the right-hand side is the fractional change in resistance after 100 thermal cycles. And what you see is the typical ALBSF and the ALBSF with these metal matrix composites, and the median is much lower for these ALBSF composites. So we do need to look at this further and in a larger scale and built up into PV modules. But this might be a way to kind of mitigate these small cracks in our metallization. Another thing to think about is multi-wire interconnection. So these are bus barless interconnections with multi-wires. So I think about 18 wires, and they still have front metallization fingers. One driving force behind this is, again, as Gerno had said, is you want to reduce the amount of silver used. Silver is expensive. Just like the number of increase in bus bars, we can decrease the amount of silver used. It also increases the cell area, so we have better light capturing. And these multi-wire interconnections are nice because you can actually do this at a much lower temperature. And that's beneficial for silicon heterojunction cells because they like to be at a lower temperature. So this bottom figure you see is that as we go from 4 bus bars to 6 bus bars with typical soldering, we actually reduce the amount of silver that's laid down. We're going to talk next about electrically conductive adhesives on the next slide, but again, that also reduces the amount of silver used compared to typical screen printing. And then these multi-wire interconnections have much less silver. And what we see here is that there is pretty low max power drop in these 72 cell modules after damping and thermal cycling with these multi-wires. So this was really nice preliminary work that these are actually decreasing the cost by reducing the silver, as well as potentially increasing the power that we can get out by increasing the surface area, as well as not degrading faster. So the next thing, when you think about connecting, is electrically conductive adhesives. So these are adhesives filled with conductive particles. They're generally polyamides. And then again, silver is the most common conductor, but you could use gold, nickel, copper, tin. And the advantage to this, again, is there's no bus bar, and it enables interconnection techniques such as shingling or conductive backsheets. And this is helpful when we're thinking about these new architectures or these new ways of incorporating PV. So if we can do shingling or have these odd shaped PV designs, that allows us to integrate PV into different applications much easier. And there's also low temperature processing, higher resolution printing, and easier handling. And there's less thermomechanical stress on cells, this technique. So potentially you can have thinner wafers. And another added value to this is that there's no need for lead. So there's no more of the lead solder in this case. So these are this is one study on electrically conductive adhesives. And one thing that's found is that the chemical composition and the cure conditions, and as well as handling these materials, actually impacts their fracture behavior. So there is some variety in what's being reported out in the literature of reliability of these, and it seems to be material handling or manufacturing the materials. In this study as well, migration of the hardener into the surrounding encapsulant material was the only migration. There was no silver migration out of the electrically conductive adhesives, and there was no harmful interactions between the ECAs and encapsulants tested, EVA, TPO, and POE. That means it seems to be very well incorporated with these different types of encapsulants that are starting to be used more often. And then our last material is backsheet, which is typically a polymer backsheet on the back. Sometimes there's glass and glass modules. And the most common backsheets are PET PVDF or PET PVF. And again, as Gernot had said, they are trying to remove these fluoropolymer-based materials because they're more expensive, and to these fluoropolymer-free. And we can manufacture those by laminating, co-extruding, or a monolayer of material. So one new kind of technique out there is transparent backsheets, and these are important for bifacial modules, which are already being deployed commercially and used. And instead of a glass back, you can use this polymer back. And this is easier transportation because they're thinner and lighter, so you can install a little easier. And they also have diffusion of water, oxygen, and acetic acid, much easier out of the material than compared to glass. And what you see here in this bottom figure is for PVF, which is right now the most common transparent backsheet, is that there's a new and an old version, and it appears the newer version has a little better UV absorbance performance, slightly less yellowing, although this yellowing here is only up to 1, which is a very small amount of yellowing. And it still has pretty good elongation at break. And under accelerated exposures of xenon and UV A fluorescence, it still has pretty good performance up to 300 kilowatts hours per meter squared. This is something that we would like more information on how it's incorporated into, say, a mini module, a full scale module. one of the challenges of these transparent backsheets is that you have to remove the TiO2 that's typically added to backsheets that protects that PET core. So you still need to be able to protect that PET core if there's a PET core or any inner layers. And then oftentimes they're adding a white grid layer to protect between the cells so that between the cells isn't completely transparent. And then again, as Gernot talked about, polyamide was one of these failures it was in 2010. And we moved away from PVF and PVDEF to these co-extruded polyamide. And co-extrusion helps where we can have much better thickness optimization. You reduce the number of processing steps, and you can be a little more selective on permeability. So you could permeate high acetic acid out while not necessarily allowing a lot of water into the module. But as we knew with our first co-extruded backsheet polyamide, what we got is a lot of failures. So Gernot went over this a little bit, but I want to touch on this again, is that the degradation mechanisms in these failures are not exactly the same, right? So we have micro cracks, which aren't pictured here, but those happen at local areas where there's a little more stress in that local area, and there's a little tiny crack, but it's generally just that outer air side surface of the backsheet. While these longitudinal cracks happen just over the bus bars, and that's due to a change in height over them. So then there's tensile stress due to that little slightly change in height, and that's where you get these cracks. And these cracks are happening again from the outside air side of the backsheet in. And when we see these square cracks, those are happening between the cells. So then they are happening from the inside, that inner layer that's facing towards the sun, out of the PV module. And so this has been found in other cases as well. And so this is a picture right here of so the glass is shattered in this module from us cutting it up. But you can see these cracks here in between the cells. And this is a polyamide backsheet. And what you're seeing happening is that there's higher irradiance happening there. There's a difference of temperature, and you're forming acetic acid in that EVA, which is then potentially attacking the polyamide and starting those degradations between the cells. So one thing when we're thinking about stressors on a PV module, the stressors within the module itself are not uniform. So in between cells, in this case, is causing a degradation feature that wouldn't have happened, that's not happening on the areas of the backsheet that are behind cells. Another thing that has been found is that the microclimate of where the PV module is installed actually impacts what is happening to the material type. So what we found here, this is a field study of a PV site, and the blue dots here are the top row. And what you see here is there's significantly higher yellowness index on the top row compared to the bottom row. And each of the sides has an edge effect where there is much higher yellowness index on the sides of the modules compared to the modules in the center. And when we measured rear side irradiance, you actually see the same exact pattern in rear side irradiance, where rear side irradiance on the back that's reflected off the ground and back onto the backsheet is actually higher on the edges and at the top of the module rows in this case. This can be different though, based on your climatic zone, the angle of light, whether there's snow on the ground, which may actually increase reflection or albedo. So where a module is actually installed on a PV site is important. That microclimate of where the PV module is installed can actually cause more or less degradation in the materials. So we also need to think about macroclimatic zones, but also how we're designing our PV sites to potentially reduce some of these materials degradation. Another thing that we found is that NO2 causes yellowing of polyamide, and this is found from the fabric industry. Knew this well before, that polyamide actually starts degrading because of NO2 degradation or NO2 pollution. And what we see here is that modules that we retrieved, these polyamide that we retrieved from Changshu, China, which had extraordinarily high amounts of NO2 concentration, actually had much higher yellowness index than the same modules at the same year retrieved from Thailand, Italy, or Arizona. So we believe that we need to consider pollutants as part of the degradation of our materials. And that, again, albedo changes really matter. So on a roof, you had much more degradation than, say, on grass. And then quickly, I'll go through, this is a study on just backsheet laminates. So they were exposed, we had 23 different backsheets, 12 suppliers, and 9 different layering combinations. And we exposed them to accelerated exposures, which was just hot UV irradiance, and then cyclic UV irradiance, where we had 4 hours of dark condensing humidity. And then we also put them outdoors in Cleveland with natural full spectrum light, and then with concentrators on them to increase the irradiance. And we got cracks that look like this on the back sheets, which are cracks that we see from PV modules as well. This is a little GIF where we can see that you can start seeing cracks forming. So the square little green dots are cracks. And you could start seeing cracks forming about 500 to 1,000 hours from the inner layer, the EVA, to the core. So all of these actually crack from the inside to the core PET, where the outer layers were actually exposed to the light. So we had inner layer cracking first. And what we found is we didn't get polyamide cracks, just like a lot of the accelerated testing didn't see that polyamide cracked. And that's because we just had films and they didn't have that stress that they have inside laminated module where there's different stress conditions. So just studying the materials and of themselves is really important to understand what's happening, but you have to add the added layer of that physical mechanical stress that happens when you incorporate materials into the PV module. And what we found is that there was very little cracking at just our 1x outdoor exposure with one backsheet type crack, but that was only for 12 months. And so it was PVF PET EVA layer. So it was this FPE2. And what we also found is we got a lot more cracking when we had the cyclic exposure that caused the most cracks. So again, as Gernot was saying, we were incorporating UV plus a thermal shock with going to condensing humidity and changing temperatures. So we need to be able to understand what's happening in our material, be able to quantify those differences that are happening due to different mechanisms of degradation, as well as being able to modify these accelerated exposures and then observe real world exposures as well. So to conclude, new materials show great promise to reduce costs, increase lifetime. In our ST 1.1 report, there is a lot more examples of new materials, but we need to be aware of those interactions between materials. Encapsulant and backsheets degrade and they're interrelated to one another. Temperature ranges needed for lamination can impact different cells. Different grades of materials, different crystallinities, and the quality of additives matter as well. And it's really important to obtain real-world data on our materials, components, and the system, and also look at accelerated stressors that mimic real-world degradation. And new materials need to first consider reliability, durability, and lifetime, which may not always be the same as the most cost-effective option. So again, I'd like to thank the collaborators who wrote this report, especially Gernot and Josh, who were the editors. And thank you very much.
Okay, great. Thank you. Thank you very much for your presentation. I will